Greetings. So, welcome to today's class. So, in today's class, we will look at another so-called structural property of dynamic systems when we look at the state space representation, and this is what is called as observability. Okay, so we'll define what this is and what is its physical, practical connotation, and how do we then evaluate it. Okay. So if you look at what are called typically called structural properties, we would have looked at stability and controllability. Okay, so we are talking about the state space representation. People always talk about stability and then controllability. Observability is another so-called structural characteristics or property. Okay, when we are considered the state space. So let's see what this is. Okay, so let us consider the state space representation of a standard single input, single output LTA system. Okay, x dot t is equal to ax plus eu, y of t is equal to c dot x plus. Okay, so this is a standard state space representation. Okay, of an LTI resource. So if we look at the solution to the state equation, we recall that the state vector, that is, if we solve the state equation, the state vector becomes e power at x0 plus integral 0 to t e power a t minus tau d u tau d tau. Okay, so essentially that's what we'll have as the state equation. Right? Sorry, solution to the state equation. And why are we discussing this to begin with? Like just connecting it to where we stopped in the previous class. We saw that if you want to implement the full state feedback controller, we require knowledge of the state vector, right? Isn't there? The implementation of the full state feedback controller requires the knowledge of all state variables. However, the question is, how do we get them, right, in real life? So that becomes a challenge, right, isn't it? So that's where, like we look at what are called state estimators, and that's where observability comes into play. So suppose if we have a 10th order system, right, and there are 10 state variables, right? So 10th order in the state spaces, right? So let's say there are 10 state variables. Now we can't practically put one sensor to measure each state variable, right? So it cannot be feasible at all. So then the question is, how can we get the most information from the least possible set of measurements from limited measurements? Okay, so that is the motivating question. So in fact, immediately we observe that when we have the state equation, okay, we essentially have two main components, okay, as far as the calculation of the state equation is concerned. One is the initial state x naught, another is the input u, okay. So typically the input u is known to us, right? But what about the initial state? Okay, so if we know the initial state, observe that like we are in a position to calculate the state vector at each and every instant of time. How? Because we have this expression, right, for x of t. If we know x0, we can calculate x of t at each and every what is the input provided to the system, correct? So once we have that information, what we need to do is just substitute this, right, into the equation for y, and then we know like how the output say, comes about, right? So the point here then becomes is that, like, if we have this knowledge of initial state, we are pretty much having a knowledge of what is happening to the system state and output at each and every instant of time, right? So that is a very important, what to say, aspect, right? So that we need to infer, right, from this equation, right? So now we are going to write down a definition, but as I mentioned, the question, the overarching question that motivates this notion of uh, observability is that, can we estimate, okay, x of p from limited measurements? So, see, for example, yesterday we were discussing the example of the quarter car model, right? So, where we have a sprung mass and an unsprung mass, right? And if we recall the state space representation of the quarter car model, we had four state variables, right? The vertical displacement of the sprung and unsprung mass, those are two state variables, and the speed of the sprung mass and unsprung. Now, if we were to implement a controller for the quarter car model to control the ride response of a vehicle, then we would require the measurements of all these four state variables. But that cannot be feasible in practice, right? Isn't it? That is where, like, we ask ourselves the question, is there a way to estimate all the state variables from the least possible number of measures? Okay, and the notion of observability is related to that. Okay, so let me define what this notion of observability is. Then we will see that we can connect all the concepts. Okay, so let me write down the definition. A dynamic system is said to be completely observable at time t naught. Let's say we take some time instant t naught. If there exists a finite time interval t naught to t1, with t1 greater than t naught. Okay, so we have a finite time interval t naught to t1. Okay, with t1 greater than t naught, such that the knowledge of the output in this finite time interval, output y of t, right? Typically, the output is measured, right? In this finite time interval is sufficient to completely determine the initial state, xt. All right. So this is the definition of observability. Okay. So the point is, the key thing is that, like, if we can determine this initial state xt naught, okay, then we can essentially know the state vector at each and every instant of time. How? From this equation, right? Is it right? Because that's the equation for x of t, which has x naught and U, right? So if I know the initial state, then like we are all set, right? Isn't it? Because we are essentially in a good position, wherein we are what to say, having the knowledge of the state vector at each and every instant of time, and consequently, like we are able to completely understand what is happening to the system from limited measures. Okay, so that is the what is the idea. Okay, so typically, in fact, due to this reason, if we want to connect these two structural properties, controllability, okay, has can be correlated to the selection of actuators, okay, in practice. So if you what to say, ask, hey, okay, what do these mathematical analysis finally lead to, right? So we can use this mathematical analysis, to figure out how I should place some actuators in a meter, right, or in the system. Okay, observability typically tells us what to measure. So physically, like it helps us to choose sensors, okay, or in sensing, okay, deciding what variables should be measured or kept, or what sensors should be installed, right, in a particular system. All right. So once again, to summarize, there are broadly what are called three structural properties: stability, controllability, and observability. Right. So controllability is something, like which is connected with controller design using the state space representation. So essentially, it helps us in choosing actuators. Okay, if you want to look at it from a physical perspective. Okay. On the other hand, the observability helps us in figuring out the state from limited measurements. So it has to do with the choice of sensors. Okay, so that is the broad physical perspective, okay, of these two character properties. Okay, so similar to uh, checking, okay, for controllability, how do we check for observability? Okay, so now, since observability has to do with the relationship between the output and the state, right? Because we are now dealing with the output and and its relation to the state vector, right? The observability criteria depends on the state matrix A and the output vector C or the output matrix C, okay, depending on whether we have a SISO system or a MIMO system. So let us first look at the MIMO system. Okay. So what happens in a MIMO system? So if we recall, in a MIMO system, the realization can be written as A, B, C, and D, right? Where all the four entities are matrices, right? And this output matrix C, if we recall, is a P by N matrix, right? Because without loss of generality, we assume that there are P outputs. So it becomes a P by N matrix. So what we do is that, like, we construct what is called an observability matrix. So what is this observability matrix? Observability matrix defined as what's the script code. What we do is that we stack all these matrices. So first we stack the matrix C, then we stack the matrix CA, okay, then CA square, all the way till C times A power n minus 1. Okay, so you can see that it's sort of like complementary to what we learned in the controllability matrix. Okay, so please note that the matrix A is n by n, right? So if you look at the observability matrix, the matrix C is P by n. Okay, CA is going to be once again another P by n matrix, right? Like that, CA power minus 1 is the P by n matrix, right? So consequently, what we are having is that if we look at the observability matrix as such, we are having n p by n matrices stacked one below the another, right? So each matrix has p rows and n columns, right? But there are n such matrices stacked one below the other. So consequently, the size of the observability matrix is np times. Okay, so I hope it is clear how we got np times, because there are n matrices which are stacked one below the other. So consequently, there are np rows. Okay, and each matrix has n columns. So that's why we have uh, the size of the observability matrix to be np times n. Okay. So what happens with the SISO system? If we look at a SISO system, and if we recall what is the typical realization of a SISO system, with the state matrix A, the input vector B, the output vector C, and the term D, right? So please note that in a SISO system, this is a vector of order n, right? This is a vector of dimension n. So what happens is this is the following. In this case, sorry, observability matrix, okay, so is defined as C A transpose C, okay, A squared transpose C, all the way till A power n minus 1 transpose C, the whole matrix transpose. Okay, so that is one observability matrix for a SISO system. So this vector C is of order n. As we already know, the matrix A is n by n. Okay, so A transpose C is the vector of order n. A square transpose C is also a vector of order n. Like this, A power n minus 1 transpose C is also a vector of order n. So consequently, this matrix O, right, observability matrix, is the matrix of size n by n. Okay, to summarize, if we have a memo system with P output, the size of the observability matrix is np by n. Okay, and if we have a SISO system, then the size of the observability matrix is n by n. Okay, so that's the construction. That's the way the observability matrix is constructed. So now, what is the criteria? Okay, so the system, okay, whether a memo system or SISO system is completely observable if and only if the rank of the observability matrix is n. Okay, so that is the uh, criteria. Okay, so we have either the SISO system or the memo system. Okay, if we have when we construct the observability matrix and we calculate the rank of the observability matrix, it should be equal to the how to say, that's the criteria we discussed. So it typically, where does it fit in, right? So as we discussed, controllability is used. Is a property which is checked and evaluated when we are designing controllers, right, using state feedback. Similarly, we use the property of observability when we want to design state estimates. Okay, so as we discussed, like we want the knowledge of the state variables to essentially calculate the control input, right? So if we use full state feedback, now who will provide us the information of all the state variables? So typically, let us say if we have 10 state variables and I have only two measurements in practice, the question is, can I get estimates of the 10 state variables by designing what are called state estimates? Okay, and that's where observability plays a very important role. And the common state estimators that we use, okay, or what are called Leuenberger observer. Okay, we are not going to go into the details of this. And another famous estimator is the Kalman filter. Okay, so typically what is called as a Leuenberger observer is used for deterministic systems. That is where there are there is no significant what is the stochastic phenomena. The system can be approximated as a deterministic system. Okay. On the other hand, if we have stochastic effects to be important, we go for the Kalman filter. All right. So that is the application. Yeah, as far as this notion of observability is concerned. Okay. So once again, the question of observability has to do with the fact that by using knowledge of the output in a finite interval of time, can one determine the initial state? And if one determines the initial state, as we have discussed, we can immediately determine the state vector, right? So then we will have knowledge of what is happening with the system, right, at each and every instant of time. And we check the criteria for observability by looking at the observability matrix, and the rank of the observability matrix should be n, okay, for the system to be completely observable. All right. So these are the key points. So now let us go and look at the same systems that we considered in the previous classes and evaluate those systems for observability. Okay, so let me go up. Okay, so first if you recall the previous class, one example that we did, wherein we evaluated that is, we essentially looked at design of full state feedback controller was this system. Okay, we will essentially look at whether the system is completely observable. Okay, so we are going to calculate the observability matrix. So I'm just going to calculate here so that we understand. Okay, so if you look at the observability matrix here, please note that n is equal to 2. Okay, so that's something which we already know. So we go only till n equals -1, right? So the observability matrix is Cn A transpose C. Okay, we go only till n minus 1 and then we take the transpose. Okay, so what is the transpose of a matrix? We interchange the rows and columns, right? So if we want to calculate the product A transpose C, first we transpose A. So this the transpose of A becomes this, right? We have interchanged the rows and columns, and the vector C is 1 and 1. So if we calculate this matrix vector product, we are going to get 2 and 2 as the answer. Okay, for A transpose. So now if we go here and then substitute for C and A transpose, this is what we get. The observability matrix is the transpose of this, so we will have 1, 2, 1, 4. Okay, and the 2 columns. So immediately we would observe that the rank of the observability matrix is 2. How? Because if you look at both the columns, right, the 2 columns are 1 and 2, and the 1 and 4, right? So we immediately observe that they are linearly independent of one another. I cannot write one column as a multiple of another column. So, and also a simple check to do is to calculate the determinant of this observability matrix, and we will find that it is non-zero, right? So we can immediately observe that it's full rank. So immediately it implies that the system is completely observed. Okay, so this is how we check for observability. Okay, so now having ascertained observability, in this example, we in the previous class we looked at what to say controllability also, right? And we evaluated the system is also completely controllable. Okay, so in fact, a realization which is both completely controllable and completely observable is what is called as a minimal realization. So if you recall, when you initially started discussing state space, I told you that later on we will learn what is called as minimal realization. So minimal realization is nothing but something which is both completely controllable and completely observable. Okay, and sorry, and why does this minimal realization become important for us? Okay, the reason is the following. If you recall the what to say relationship between the eigenvalues of the state matrix and the poles of the transfer function. If you recall, I would have made a comment, right? So for a minimal realization, the eigenvalues of the state matrix are the same as the poles of the transfer function. Okay? So that is a very important result for a minimal realization. For a non-minimal realization, what will happen is that the poles of that transfer function will be a subset of the eigenvalues of the state matrix. You know, we saw something called as a pole zero cancellation a few classes back, right? Wherein, you know, like we did have two eigenvalues, but only one pole, right? So that is an example of a non-minimal realization. Okay, but a minimal realization, which is one which is both completely controllable and completely observable, will have that unique property. That is, it will have the eigenvalues of the state matrix being the same as the poles of the transfer function. Okay, the set will be the same. Okay, so I hope the concept of minimal realization is now clear. So now we will also evaluate observability for the other example that we did in the previous class. Going to the next example, okay, we did this, right? So let's evaluate the once again the observability matrix O will be C and A transpose C, right? The whole thing transpose. Once again, N is 2 here, right? So if you look at it, the value of N is 2. So we go to N minus 1, it is only 1, right? So C will be 1, 0. What about A transpose C? Okay, so once again, if we have to evaluate A transpose C, so if you evaluate A transpose C, what do we get? The transpose of A will be 0, 1, and 2 and minus 1. Then C will be 1. Okay, so if you multiply this, we are going to get 2, 1. All right, so that's what we are doing. All right, so A transpose C. Oh, sorry, no. I think, sorry, not 2 and 1, 0 and 1, right? Yeah, sorry, I made a mistake. It's 0 and 1, right? Not 2 and 1. So A transpose C, if I multiply this, you will get only 0. So immediately we can observe that the observability matrix is just the identity matrix. Okay, 1, 0, 0, 1. and the rank of this matrix is anyway 2, right? So it has full rank. Okay. So once again, the system is completely observable. And we can immediately see that this realization is once again minimal, right? Because the previous class we observed that we found out that this system is also completely controllable, right? So that's something which we have already determined here, right? So we have what is called once again a problem also corresponds to what is known as a minimal. Alright. So I hope this concept of minimal realization is clear, and what is the corresponding value. Okay. So this is how we calculate or evaluate what to say the observability of a system. So once again, to summarize, observability has to do with the fact as to whether we can get knowledge of the state variables from limited measurements. Okay, so that is the physical, what to say, perspective, right? So if you look at the physical perspective of controllability, what you are asking is whether we are in a position to regulate or take the system state from any initial there is any initial state to the equilibrium state in finite time, right? So that's how we sort of visualize controllability, right? Observability has to do with the fact that whether we are able to get the idea about the state variables from measurements, right? Limited measurements. Okay? So consequently, we framed what is called as the observability matrix, and the rank of the observability matrix should be n for what is the system to be completely observable, and the application of observability is in the domain of what is designing state experiments, such as the Leuenberger observer and method. All right, and a realization which is both completely controllable and completely observable is what is called as a minimal realization. Right? Okay. So these are key concepts. So now, what I am going to do is that I'm just going to motivate the next question, which we will complete in the next class. Okay, on how do we design this full state feedback controller in an optimal way. Okay, so recall that for a full state feedback controller, u of t, right, the control equation is going to be equal to k times x of t. Of course, see in the examples that we looked at yesterday, right? So we calculated k by considering some location of the closed loop eigenvalues, and we obtained the value of k. Okay, that's fine. All right. But however, if one were to ask, how do we optimally, how can one optimally choose control gain? Okay. Okay, so that is an important question, right? So essentially, we want to ask ourselves, amongst various full state feedback controllers that we can design, right? How do we essentially sort of figure out which is the what to say most optimal one, right? So that's what we want to okay. So consequently, it is essentially the question of designing the controller subject to some framework, right? Some design framework, right? So the point is, how do we get the control gain K such that we satisfy some constraint or minimize some performance metrics and so on, right? So one a very popular uh, optimal controller in this uh, perspective is what is called as the linear quadratic regulator, okay, or LQR. Okay, so which is something which we will learn in the next class. Okay? So we will figure out what this linear quadratic regulator is, and then you have we will essentially figure out, like how do we design the controller such that a specified performance metric or performance index is minimized, okay, subject to some requirements. All right. So we will see how it is used. All right. Okay. So these are the concepts that I wanted to discuss in today's class. Are there any questions? So if not, I will close today's session here, and then we will continue in the next class. Thank you.